Hey there, in this video I want to talk about solving second order ordinary differential equations, and the techniques that we work here could be extended to third order and above. It's just, in practice you usually don't see more than second order equations out there in the wild. Okay, so by second order ordinary differential equation, what I mean is that second derivatives show up into it. Maybe first derivatives do as well. So this would be an equation that looks like d2x dt squared on the left hand side equals some combination of x's dx dt's and time. And I suspect the parentheses are going to look really ugly when I try to render this. Yeah. So if we add this slash left and slash right, it'll make it look pretty. I mean, not that that's really important in this class, but just FYI. So this is a second order differential equation. And the trick here is to make this into several first order differential equations. And then since we already know how to solve simultaneous equations, we're good to go. And the way we can do that is start with the definition of the second derivative here. Like, let's say that we define dx dt to be equal to v. So sort of thinking something like velocity. If that's the case, then we could rewrite the second order part of this as dv dt. And that was equal to f of x, its derivative, which we're calling v now, and time. Okay, so this single second order equation is the same thing as two coupled first order equations. And so, I mean, this is generic enough a technique that we could go third order and, as far and crazy as you wanted to. And we could do simultaneous second order equations, we just have more equations. Okay, let's try an example. Let's do the pendulum, the not simple pendulum. So you learn in intro physics that a pendulum has a constant period no matter how far you pull it back from the starting point. Well, as long as you don't pull it back too far from the starting point. We call it small angle approximation. Let's just do the full thing where we don't have small angle approximation. And so the differential equation there for our pendulum is going to look like d2 theta dt squared is equal to negative g on L. Let's just say that g and L happen to be 1. So, I mean, I guess this is like a 9.8 meter long pendulum, but, I feel lazy with units. So we'll make it negative, just negative 1 here. And then on the right-hand side of the full equation, we technically have a sign here because this comes from torques. So we're going to have a sine of theta. I keep forgetting to turn these into markdown cells, so it keeps yelling at me. Okay, so this is the equation we're going to solve. This needs initial conditions. So let's make our initial condition theta set by a slider, and then we'll see what happens when the angle goes from small to large. And we'll test the idea of whether or not the period is constant or when the period stops being constant as we make the angle larger. We also need a second boundary condition or initial condition. And that's because we have two equations here. If you have two equations, you have to have two initial conditions. And so we have an initial condition for x, which is called theta, for the pendulum problem. And we need an initial condition for its derivative. So that would be the angular velocity of our pendulum. Let's say that that's going to be 0 for us. Basically, the pendulum starts from rest at some angle we pick. All right, so first thing we need to do is define a function here for the right-hand side of the equation up here. I mean, technically it needs to be the right-hand side of both equations. If you remember, the way we handle simultaneous equations is I'm highlighting the wrong things, these two. The way we handle simultaneous equations is we pretend it's a single equation that we give an array to, and we get an array out of. So we're going to give an entire array of variables r as a function of time here. First thing we want to do is unpack it. So we'll call th here will represent theta, w will represent omega. And we will unpack those from the array r. And then we have two functions. We have a function for theta, and we have a function for omega. And then when we're done, we want to return those. And remember, we want to return those as an array so that our function is going to work. So our Runge-Kutta function is going to work. We'll have our f theta and our f omega returned. Okay, now this is all basically generic stuff. What are those functions going to be? Well, so a function of theta, that means that d theta dt equals, well, d theta dt equals omega. What about d omega dt? D omega dt, that's what's written right here. D omega dt equals negative sine theta. So we'll just let that be in its own cell. Okay, so now we're going to write code that should start to look very familiar. This is kind of our basic technique for solving differential equations. We define a step size. We set some values. For our time, let's go from 0 to 20 seconds in steps of h, which will be 100th of a second. And I'm just making those values up. It just, it feels like it should be enough time for this thing to swing back and forth. It feels like this h should be small, I mean, especially compared to the amount of time we're doing. But we can adjust any of these if we need to. And now, if I'm going to use a slider here to set theta, what I want to do is I want to write some code here, a function whose job is to solve the differential equation and plot it. So let's call that code, or that function, pendulum. It takes a single argument theta initial, which will be set from a slider. Now, in this code, we need to set our initial conditions, which are not always going to be the same. I mean, that's the whole idea of having the slider. So we're going to start with theta equal to theta initial, and omega is always going to be set to 0. We're going to build some empty lists that we're going to fill in, one for theta, and in principle, we could make one for omega as well. I'm just going to plot theta. So I'm not actually going to use this list. I'm going to fill it in anyway, just to show you, where that would show up in the code, but I'm not actually going to use it for anything. And then for t and t values, our basic sort of loop. Step 1, append values. So we'll do that with theta and omega. Again, I'm not really going to do anything with the omegas. So you could leave that line out and it won't change anything. And now we need to update theta and omega. We get those by calling that function we wrote, rk4. It starts with the function. It wants some kind of sequence of values. A tuple will work fine, an array would work fine. It gets the time and step size h. And that's it, that's our for loop. Now, so far, this function just calculates things for us. It doesn't actually show us anything. I would like to see something when I run this code. So we're going to make a plot of theta with respect to time. And since I'm going to be changing stuff with a slider, I don't want my graph to jump around. The x range on my graph is going to be set by these time values, so that's going to be stable. But the y range is not going to be stable. It depends on what the amplitude of the pendulum is. So let's fix that to -pi to pi, because that's the biggest range theta can have. And that's just to stop things from scaling. Okay, and then we will tell it to show our function. And now finally we need to write some code to make a widget and display it for us. So we need to import ipy-widgets. We need to import display from IPython. We need to make a slider. So this will come out of widgets. Thetas, I think, are going to be floating point values here. Something like float slider, I think. Is my tab complete? Well, I'm just going to go with float slider, and it can yell at me if that's wrong. We'll make our minimum value 0, our maximum value will be pi, our step size will be 0.1 I think would be good enough there. And then we're going to create the visible widgets using interactive. We want it to call the function pendulum, and we want to set the argument theta naught to the result of our slider. Finally, we want to display it. Okay, it is mad. Is it the name? Widgets is not defined. Import. Oh, yeah, okay. I'm used to calling it widgets, so we'll just add this line here. IPy widgets as widgets. That explains why tab completion wasn't working. List object has no attribute appends. Oh, because I spelled append wrong. Up here. I didn't even need the omega. Look at that. And it ended up burning me. All right, so here we go. Here's our slider. I'm just going to use my arrow keys to change it. If we start with the pendulum pulled back not at all, then of course we don't have any amplitude. And now as we start pulling it back some small amount, this would be units of radians here, we can see, you know, for 0.2, 0.3, 0.4, 0.5 radians, the period looks pretty constant. But as we continue to pull it back and we approach 1 radian, we start to see the graph shifting over to the right because we are leaving the small angle approximation. And here we get to, this would be about pi on 2, so this would be 90 degrees. And then we can even pull the pendulum back till it's nearly vertically upwards, all the way up to almost pi. And we can see that the period has become huge compared to what it used to be. And it's not really a sine wave anymore. It's really kind of flat down here at the bottom. Now, I guess that's not the important thing. The important thing here, though, is that we took a second order ordinary differential equation. We split it apart to make 2 first order equations, and then we solve things like they were simultaneous first order equations.